Tectonics of the Philippines. This report focuses on the structural geology and tectonics of the Philippine archipelago. We'll break down the key geologic components, explain how different land masses came together, and examine why the Philippines is one of the most geologically dynamic countries in the world. Let's talk about the Philippine geologic overview. We begin with a broad overview of the country's geologic setting. The Philippines sits at the boundary of major tectonic plates, which explain its active landscape, frequent earthquakes, and numerous volcanoes. Understanding the basics of its structure is essential to appreciating the risk and richness of this region. And the ongoing geological activity and its relevance. The Philippines continues to experience active tectonic movements, like frequent earthquakes and volcanic eruptions, show that the mobile belt is still shaping the land. So, tectonic activity in the Philippines is not a thing of the past. We continue to feel the effects of this movement through earthquakes and volcanic eruptions. These events are signs that the mobile belt is still changing the shape of the country. So, some examples of these ongoing activities is the 1990 Luzon earthquake, 1991 Mount Pinatubo eruption. Over 20 active volcanoes and regular seismic activities are recorded nationwide. These real-life events highlight how active the Philippines still is geologically. The Luzon earthquake and Mount Pinatubo eruption caused widespread damage and are just two examples of many. With over 20 active volcanoes and frequent tremors, the mobile belt continues to reshape the country. And now, there are two main entities. In general, the Philippine archipelago can be divided into two geologic entities, namely, the Philippine Mobile Belt and the Palawan-Mindoro Microcontinent. The Philippines is made up of two major geologic blocks. The Philippine Mobile Belt forms the central spine of the country and is highly active tectonically. Meanwhile, the Palawan-Mindoro Microcontinent is older, more stable, and geologically distinct, having originated from the Asian mainland. So, the first one is the Palawan-Mindoro Microcontinent. The Palawan-Mindoro Microcontinent is a geologic block that was rifted from the Asian mainland during Cretaceous and late Eocene time and drifted to approximately its present position with the opening of the South China Sea basin. This block was once attached to mainland Asia and started drifting away during the late Cretaceous to Eocene period, around 70 to 34 million years ago. The drifting was caused by the opening of the South China Sea, which pushed back the block towards the Philippines. Today, it formed parts of Palawan, Mindoro, and nearby islands. And the Philippine Mobile Belt origin. The Philippine Mobile Belt is the group of land masses that apparently originated from sub-equatorial regions to its present position, with the rotation and spreading of the Philippine Sea Plate during Eocene to Miocene times. Unlike the Palawan block, the land masses in the Philippine Mobile Belt came from near the equator. These fragments were transported and reoriented by the movement of the Philippine Sea Plate between the Eocene and Miocene, which spans roughly 56 to 5 million years ago. This complex movement is the reason the Philippine Islands are geologically diverse and fragmented. And now, moving on to the lithologic units. Each of these two entities is composed of different types of lithologic units that can be classified into four general groups, namely, first, metamorphic rocks, second, ophiolites and ophiolitic rocks, third, magmatic rocks and active volcanic arcs, and lastly, sedimentary basins. All Philippine rocks can be grouped into four major types. Metamorphic rocks were formed under high pressure and temperature. Ophiolites represent ancient oceanic crust pushed onto land. Magmatic rocks form from cooling magma and include volcanic material. Sedimentary basins contain accumulated layers of sand, mud, and fossils. These different rock types reflect the various geologic processes that shape the islands. So now we will be talking about the Philippine Mobile Belt. the Philippine Mobile Belt. This belt is a major tectonic feature in the Philippines, where most of the country's earthquakes and tectonic activity happen due to its location between two major plates. So here in this slide, we can see the simplified figure of tectonic map of the Philippines. So it shows a simplified map that highlights the major tectonic structures in the Philippines. It includes key features like the Philippine Trench, major fault lines, and blocks such as North Palawan Block. The map helps you visualize how the Philippine Mobile Belt fits within the overall tectonic layout of the region. The boundary between the Philippine Sea Plate and the eastern margin of the Eurasian Plate is a complex system of subduction zones, collision zones, and the marginal sea basin openings. This slide explains that the Philippines lies between two massive tectonic plates, the Philippine Sea Plate and the Eurasian Plate. Their interaction is complicated and involves subduction, where subduction is where one plate is sinking under another, collision, where plates crashing into each other, and the creation of small sea basins. These complex processes are responsible for the country's active geological nature. In between these two plates, an actively deforming zone is created. This zone represents the Philippine Mobile Belt, a term first defined by Gervasio. Here the slide describes what happens between the two tectonic plates. The constant movement and pressure create a zone where the Earth's crust is continually deforming. This deforming area is what we call the Philippine Mobile Belt. It was first named by a scientist named Gervasio in 1966. And now let's talk about the importance of the Philippine Mobile Belt. It formed the Philippine Islands, mountains, and volcanoes caused by the movement of major tectonic plates, explain why the country has rich natural features and frequent earthquakes. It continues to define the Philippines' dynamic landscape and geological identity. The Mobile Belt is essentially the heart of the Philippines. Its continuous movements explains how our islands were formed, why we have high mountains and volcanoes, and why we experience so many earthquakes. This region is not just geologically important, it's also too central in understanding our risks and resources.
So let's now talk about the cross-section of Philippine subduction zones. So this cross-section, as we can see in the figure given, is the fundamental process driving much of the Philippines geology, which is subduction. So here, the denser oceanic crust of the Philippine plate is forced beneath the lighter continental crust of the Eurasian plate at a subduction zone. So this process occurring where these plates converge is a major source of earthquakes and volcanic activity in the archipelago. We know that lithospheric and asthenospheric mantle is the layers crucial for understanding plate movement. So general geodynamic framework. So the Philippines is generally interpreted as a collage of insular arcs, aphylitic suites, and continental rocks of Eurasian affinity. So as we can see in this figure, it provides a broader view of the Philippines tectonic setting. So it is located at the complex intersection of major plates with the Eurasian plate to the west and the vast Philippine Sea plate to the east. We can observe that the Manila Trench and the Philippine Trench mark the surface expression of these subduction zones. Also, we know that Philippine fault is a significant strike slip fault accommodating the horizontal plate motion. Meaning, Philippines is essentially a geological collage or an assembly of volcanic island arcs, aphylitic suites, and continental rocks with Eurasian origins, all brought together by these dynamic plate interactions. Now, let's proceed to upper life. So it is the remnants of oceanic crust and upper mantle that have been thrust onto continental crust. It is also the widespread of occurrence in the Philippines, often found together with two tertiary metamorphic rocks. Also, it represents basement rocks upon which magmatic arcs develop. What is opulites? So, opulites are crucial geological marker in the Philippines. They represent fragments of oceanic grass and the underlying upper mantle that have been thrust onto continental land. Their widespread presence, often alongside ancient metamorphic rocks, indicates significant past tectonic events. Furthermore, opulites often form the foundation upon which volcanic island arcs are built, providing insights into the sequence of geological development. So now let's explore typical opulite. So typical opulite is a complete opulite sequence as shown here in the figure. It is consists of distinct layers representing different parts of the oceanic lithosphere. So from the top we have pelagic sediments, deep sea accumulations, while in the below we have the below basalts that is formed by underwater lava flows, and next are the intrusive igneous rocks, which are the diabase and gabbro, which cool beneath the ocean floor. And lastly, at the base, we have the tectonized peridotites. So it is the rocks from the Earth's mantle. So, moreover, identifying these layers help geologists understand the structure and composition of ancient ocean basins that are now exposed on land. Now let's shift our focus on distribution of opulites and opulitic rocks in the Philippines. So this figure illustrates the distribution of opulites and opulitic rocks across the Philippines. Notice their occurrences in regions like Eastern Luzon, Palawan, and parts of Eastern Mindanao. This distribution pattern is not random. It reflects the complex history of tectonic collisions and the abduction, or yung overriding of oceanic crust onto different parts of the archipelago over a billion of years. So the varied locations underscore the diverse tectonic events that have shaped the Philippines. Now let's focus on the age and metamorphism of opulites. So dating of opulitic rocks is based on the ages of the pelagic sediments covering them. So ages vary from early late Cretaceous to Oligocene, such as the early late Cretaceous. Example of this is the Northeast Luzon, Montalban, Eocene, which is the example of Palawan and Zambales, and Oligocene, which is Mindoro. And also we have the metamorphism. So metamorphism is the portions of opulitic bodies that have undergone varying degrees of metamorphism. So in pre-1980 literature, they were sometimes referred to as ultramafic complexes or undifferentiated Cretaceous Paleogene basement. So structural nature and origin of opulites. Structural nature. Opulitic rocks are generally crossed over Paleogene sequences in various locations across the Philippines. Origin and emplacement. The origin and mode of emplacement of opulites are still debated. Examples of differing interpretations. Zambales opulites, Philippines and Everett's 1983 disregarded origin from the South China Sea. Oligocene, Miocene age, Humol and Datwin 1990, which is the proposed origin from Pliocene to Eocene to South China Sea, which is the existence of which is debated. Also have the Mindoro Panay opulites, more clearing story Oligocene age, correlates to cross of the South China Sea, which involved in collision between Palawan, Mindoro, and microcontinent and the Philippine mobile belt in the Miocene. We will now proceed to discuss sedimentary basins. So, sedimentary basins are depressions in the Earth's crust where sediments accumulate over time. So, these basins form due to various tectonic processes, including tectonic subsidence such as sinking of the crust, rifting or the pulling apart of the crust, flexure due to the weight of geological features, and movement along seismic faults. So, the accumulated sediments within these basins can include plastic materials like sandstones and shales, carbonate sediments such as limestones and organic matter, which has implications for resource potential. So we also have the Philippine sedimentary basins. So depressions in the Earth's crust where sediments accumulate over time. So these basins can form due to a variety of tectonic processes. including tectonic subsidence, lifting, flexure due to loading, strike slip faulting, and accumulated sediments within these basins can include various materials such as declastic sediments or yung sandstone shales, carbonate sediment, which are the limestone, and also yung organic matter which can lead to the formation of hydrocarbons. So let us now turn our attention to orientation of basin axis. So in the Philippines, sedimentary basins generally exhibit a north-south orientation of their axis. However, there are significant exceptions. So for instance, the Mindoro and southern Luzon basins are oriented more northwesterly, while on the other hand, the Panay and Visayan Sea basins show a northeasterly trend. So these variations likely reflect the complex interplay of regional tectonic forces. Furthermore, these basins contain a substantial amount of sedimentary cover, having thicknesses ranging from 4,000 to 12,000 meters, and they cover extensive surface areas across their archipelago.
Good day everyone. Now, I'll be discussing the Palawan Microcontinental Block, a unique geological feature found in the western part of the Philippine archipelago. The Palawan Microcontinental Block, or PMB, is a continental fragment located along the western margin of the Philippines. The map on the slide shows the tectonic settings of the Palawan Microcontinental Block, highlighted in green and enclosed within the red circle. This continental fragment includes Palawan Island, parts of Mindoro, and the Calamian Islands. Unlike much of the Philippines, which is mostly volcanic in origin, this block is continental, believed to have once been part of the mainland Asia. Now, it's embedded in the complex tectonic setting of Southeast Asia, lying adjacent to the features like the Philippine Mobile Belt and the Negros Trench. This slide shows two detailed geological maps of Palawan, highlighting the different rock formation across the region. Palawan's geology includes metamorphic basement rock such as schist and gneisses, covered by granitic rocks, a signature of continental crust. The colored region in the map represent various formations such as limestone and sandstones, which suggests shallow marine deposition. Radiometric dating has revealed that this rock formed from the Mesozoic to early Cenozoic era, linking them to the Eurasian continental margin. Let's move on to the origin and evolution of the Palawan Microcontinental Block. The Palawan Microcontinental Block is thought to have originated from the southeastern margin of the Eurasian plate and was once part of the South China Block. During the late Mesozoic to early Cenozoic, it drifted away due to the opening of the South China Sea. As shown in this geological map, the block drifted southeastward and eventually collided with the Philippine Mobile Belt. This tectonic collision led to significant uplift and deformation in areas like Mindoro and western Luzon, shaping the topography and geological structure we see today. The Philippine Mobile Belt, or the Palawan Microcontinental Block, offers critical insight into the plate tectonic evolution of the region. It illustrates how continental fragments such as the Palawan Block can move across oceanic basin and interact with island arc systems. The collision of the PMB with the Philippine Mobile Belt help explain complex geological features including the formation of accretionary prism, the uplift of Mindoro and Zambales Range, the presence of ophiolites and fault system in western Luzon. Furthermore, the PMB is essential in understanding the geological differentiation between eastern and western Philippines. This map provides a tectonic overview of the Philippines. The orange shading highlights the Palawan Microcontinental Block, a fragment of continental crust. The gray shading shows the Philippine Mobile Belt, which consists mostly of volcanic and oceanic rock. The black triangles represent subduction zones, and the direction they point indicates the direction of subduction, where one tectonic plate is diving beneath another. The Palawan microcontinental block is a unique geological feature with valuable scientific importance. Its drifting, docking, and collision history enhances our understanding of how tectonic processes occur in Southeast Asia. It also plays a role in influencing geological hazards, resource availability, and the overall structural integrity of the Philippines. Most importantly, by studying the PMB, geologists can reconstruct past plates movement and better predict future tectonic behavior.
Following our discussion on the Palawan microcontinental block, we now turn to the active trenches, a fundamental component of the region's complex tectonic framework. So in this slide, we have an image that shows the geographic setting of the Philippines in relation to several active tectonic features. So due to its position along the complex boundary of the Philippine Sea Plate and the Eurasian Plate, the country is surrounded by multiple subduction zones. So among these are the 6 major active trenches that play a key role in accommodating plate movements and generating various geologic phenomena, including earthquakes, tsunamis, and volcanic activity. So, the 6 major active trenches include the Philippine Trench, PT, located to the east. This trench marks the subduction of the Philippine Sea Plate and the Philippine Mobile Belt. Next, we have East Luzon Trench, ELT, located east of the Luzon Island. Third, we have Manila Trench, located to the west where the Philippine Sea Plate meets the Sunda Plate. Fourth, we have Negros Trench. This is located in the central Philippines, Visayas, near the Philippine Mobile Belt. And then next, we have Sulu Trench to the southwest of Mindanao and Sulu. And lastly, we have Cotabato Trench, found at the south of Mindanao. Now, let's discuss each trench in more detail, starting with the Philippine Trench. So, the Philippine Trench is a result of the westward subduction of the Philippine Sea Plate beneath the eastern Philippine Arc. The subduction angle is gentle in the north but steepens to over 45 degrees in the south. It's considered a young trench, likely formed less than 5 million years ago, and is currently propagating southward. A well-developed accretionary prism is visible along the trench but abruptly diminishes as it extends south. In terms of depth, the trench is among the deepest in the world. A sounding of 34,450 feet was recorded by the USS Cape Johnson in 1945, followed by a slightly deeper measurement of 34,578 feet by the Galatea in 1951. Next, let us discuss the Manila Trench. So this is located west of the Luzon Island and opposite of the East Luzon Trough. So this trench marks as an active convergent boundary between the South China Sea and the northern Philippines. It formed from the subduction of the South China Sea oceanic crust beneath the Philippine Sea Plate, starting in the early Neogene period. So it appears as a long and deep depression in the seafloor, reaching depths of about 5,100 meters near the latitude of Manila. And unlike the Philippine Trench, the Manila Trench has a well-developed accretionary prism made mostly of sediments, as supported by seismic and gravimetric data. A four-arc basin also lies between this prism and the Luzon Island. The subduction zone here is also steep in the south and becomes shallower towards the north, eventually connecting to the Mindoro-Panay collision zone. To know more about the Manila Trench, we have a submarine topographic map of the Manila subduction zone. It shows the locations and depths of earthquakes with magnitudes of 5 and above that have occurred along the trench. So, the Manila subduction zone is an active and relatively young subduction system where the South China Sea Plate passively subducts beneath the Philippine Plate. The Philippine Sea Plate moves northwest at a rate of about 80 mm per year, with much of that energy being absorbed along the Manila Trench. And this zone is seismically active and possesses a tsunami hazard. So from the 1970s to 2024, there have been 1,963 earthquakes with magnitudes over 5 in the region, including 137 above magnitude 6 and 17 above magnitude 7. So, most of these are shallow focus earthquakes, occurring at depths of 50 km or less. However, intermediate depth earthquakes are observed more in the northern and southern parts of the trench. Notably, around 16 degrees north, earthquakes' depths become more shallower towards the north, indicating changes in the subduction angle and trench structure. To understand the structure of Manila Trench better, we look at this figure, which shows the seafloor bathymetry and segmentation of the trench. So, the Manila Trench is divided into 4 main segments based on differences in crust type, seafloor features, and subduction processes. So, we have 4 segments, N1, N2, C, and S. So, N1, which is the color yellow, is in the north involves the subduction of thinned continental crust and is influenced by nearby basin like the Taiwan Strait and Bashi Basin. N2, color green, and C, white, are dominated by the oceanic crust, with the central part featuring sea mounts and fossil spreading ridges, creating a slab window, a break in the subducting slab. S, color orange, in the south is where pure oceanic crust is subducting, leading to stronger seismic and volcanic activity. As seen in the right side of this figure, in part B, 400 profiles were measured across the trench to better understand its structure and segmentation. This helps reveal how subduction varies along the length of the trench. Next, we look at the East Luzon Trough, named for its position just east of Luzon Island. This feature formed due to the subduction of Philippine Sea Plate beneath Luzon, yet it behaves differently from typical subduction zones. Notably, it lacks clear indicators of active subduction. There are no volcanic arcs and compressive structures, often seen in tectonically active margins, are scarce. These structures weaken significantly from 16 degrees to 18 degrees north. And because of this, some scientists propose that the East Luzon Trench is a nascent subduction zone, which means one that is just beginning to develop and may be propagating northward. Others interpret the disappearance of deformation to the north as a result of complex kinematic interactions between tectonic blocks. And to gain a clearer understanding of this region's tectonic evolution, we must also consider adjacent features. So, one key example is the Brenan Rise, located to the east of this trough. Though not part of the main trench system, its movement and interaction with Luzon provide important evidence for ancient subduction zone in this area. And the presence of an inactive accretionary prism west of the current trough and cessation of subduction-related volcanic activity in the early Miocene further support this interpretation. Now, let's move on to the Negros Trench, which is situated parallel to the western coast of Panay and Negros Island. This trench marks the subduction of the oceanic crust from the Sulu Sea Basin beneath the Philippine Mobile Belt. Unlike more pronounced subduction zone, the Benioff zone here is not clearly defined, meaning that earthquake activity does not strongly outline the subducting slab. However, seismic and geological evidence shows that the slab dips shallowly and does not extend beyond 100 km in depth. Despite the subdued seismic expression, the region does feature an active volcanic arc, highlighted by volcanoes such as Canlaon, indicating that subduction-related magmatism is ongoing. Finally, it is important to note that Negros Trench is tectonically connected to the Manila Trench. This connection is marked by shallow underwater trough that runs northeast of Palawan, linking the two trench systems in the overall subduction framework of the region. The Sulu Trench, found west of Mindanao and Sulu, reaches depths of about 5,600 meters. It formed in the early Miocene from the subduction of the Eurasian plate beneath the Philippine Sea Plate. Unlike other trenches, this area has low seismic activity and a less defined gravity anomaly, indicating weaker subduction. Volcanoes like Mount Manindang lie to the south, and the trench marks a former collision zone that helped form the Philippine Trench. Lastly, the Cotabato Trench lies off the southwestern coast of Mindanao and was formed by the east-dipping subduction of the Sunda Plate beneath the Philippine Mobile Belt. It is considered a young trench that formed between the late Miocene and Pliocene with a convergence rate of about 100 mm per year. So this trench is marked by a poorly developed Benioff zone and becomes less distinct towards the south, merging into the Molucca Sea. An active volcanic arc is present, and the Cotabato Fault links the trench to the Negros Trench.
Now, let's move on into the collision zones of the Philippines. First, Luzon Collision Zone is a geologically active region in the northern Philippines where the Philippine Sea Plate and the Eurasian Plate converge, leading to complex tectonic interactions. To understand the tectonic collision zone in Luzon, it's helpful to examine diagrams that illustrate the interaction between the Philippine Sea Plate and the Eurasian Plate. These diagrams depict how the Philippine Sea Plate subducts beneath the Eurasian Plate along the Manila Trench, leading to significant geological features such as the Luzon Arc and the Philippine Mobile Belt. Another valuable resource is a tectonic map of the Philippines, highlighting active subduction zones and the internal faults. These diagrams collectively offer a comprehensive view of tectonic interactions in Luzon, aiding in the study of geological processes and potential seismic activities in the region. Second, Mindoro-Palawan Collision Zone is a significant geological region in the Philippines, where the Palawan microcontinental block interacts with the Philippine Mobile Belt. This collision has resulted in complex tectonic features and has implications for seismic activity in the area. This map illustrates the position of Palawan at the southeastern margin of the South China Sea, highlighting how the northeastern edge of northern Palawan is colliding with the western edge of the Philippine Mobile Belt, while its central and southern sections remain seismotectonically stable. And the last one is Eastern Mindanao Fault Zone. It's a significant segment of the Philippine Fault Zone, PFZ, a major left lateral strike slip fault system traversing the Philippine archipelago. In Eastern Mindanao, the PFZ extends approximately 400 to 500 kilometers from Surigao del Norte to Davao Oriental, playing a crucial role in accommodating the oblique convergence between the Philippine Sea Plate and the Philippine Mobile Belt. To visualize the tectonic interactions in the Eastern Mindanao Fault Zone, the following diagrams provide detailed representations of the region's complex geological features. In the left picture, this map illustrates the location of aftershocks and regional tectonic settings in Eastern Mindanao. Active faults are depicted as black lines, while trenches are indicated with lines bearing triangles. The map also shows the relative plate motions between the Philippine Sea Plate and the Sunda Plate, providing insight into the tectonic dynamics of the area. In the right picture, this geologic map showcases the southern part of the Philippine Fault Zone as it divides the Pacific Cordillera and the Agusan Davao Basin. It provides a detailed view of the lithological unit and fault lines, aiding in understanding the geological structures associated with the EMFC.
And now, let's head on with the Philippine Fault. So, the Philippine Fault System, or maybe so-called PFS, is a prominent left lateral strike slip fault traversing the Philippine archipelago. It plays a significant role in accommodating the oblique convergence between the Philippine Sea Plate and the Sunda Plate, resulting in complex tectonic and structural features across the region. Understanding this fault is critical not just for earth science but for also for disaster preparedness and national planning. So the Philippine Fault System approximately is 1,200 kilometers from Luzon in the north to Mindanao in the south. In northern Luzon, the fault system exhibits a complex braided pattern within multiple plays, influencing the tectonic evolution of the Central Cordillera region. So the Philippines lies within a complex tectonic boundary between two major plates, which are the Philippine Sea Plate to the east and the Eurasian Plate to the west. This interaction forms the Philippine Mobile Belt, which is a highly deformed zone for hosting multiple faults and subduction zones. So what you see on your screen is the fault map of the Philippine fault system. So again, the Philippine fault is the fault system formed due to shear partitioning. It is a process where oblique subductions leads to both compressional and translational movements. Over millions of years, this movement created multiple fault branches, allowing the crust to adjust to the regional tectonic stresses. And what we have here are the regional variations and fault segments. So the PFS is segmented into several key faults, each with unique behaviors and risk profiles, which are named Ginayangan, Masbate, and Leyte faults, Sibuyan Sea Fault, Marikina Valley Fault System, and Lubang Verde Passage Fault System. So, Ginayangan, Masbate, and Leyte faults. These central segments are among the most seismically active, with the Ginayangan fault exhibiting slip rates of 20 to 33 millimeter per year and generating significant earthquakes approximately every 300 to 100 years. So next one is Sibuyan Sea Fault, where it is located offshore north of Masbate. This is a left lateral fault and is part of the PFS or Philippine Fault System and accommodates the oblique convergence between the Philippine Sea and the Sunda Plates. And next one is the Marikina Valley Fault System, and it is also known as the Valley Fault System. This is a right lateral strike slip fault that runs through Metro Manila and surrounding areas, posing a significant seismic hazard to densely populated regions. And lastly, the Lubang Verde Passage Fault, where this is a offshore left lateral fault system between Batangas and Mindoro Islands and is associated with seismic activity including the 2021 magnitude 6.6 Calatagan earthquake. And to sum up, this segment tells us that seismic activity is distributed but varies in frequency and intensity. So, the tectonic evolution of the fault. The Philippine fault has undergone significant tectonic evolution over geological time. Over the past 5 million years, the Philippine fault has evolved significantly. In eastern Mindanao, for example, it marks the shift from a collisional zone to a strike-slip zone, indicating changing dynamics over geological time. In the Visayas, remnants of older fault traces still influence seismicity until today.
So now, let's discuss the magmatic arcs in the Philippines. So what exactly is a magmatic arc? A magmatic arc is a chain of volcanoes that forms above a subduction zone. So a subduction zone is a region where one tectonic plate is pushed beneath another. This movement generates heat and pressure, causing parts of the subducting plate to melt and produce magma. The magma rises through the earth crust, and over time it results in the formation of volcanoes. These volcanoes tend to align in a linear pattern, forming what we call a magmatic arc. So what makes these arcs unique is their distinct geochemical signature, setting them apart from the other volcanic system. Next is the tectonic settings of the Philippines. So the Philippines sits at the meeting point of several major tectonic plates, making it one of the most geologically active places on Earth. So these plates constantly collide, shift, and dive beneath each other, which is why we often experience earthquakes, volcanic eruption, and even the slow rise of mountains. These complex tectonic settings give rise to a dynamic geological process, including the formation of magmatic arcs. So because of this, the Philippines serves as a natural laboratory, an ideal place to study how tectonic forces and magma generation shape our planet.
Let us now take a closer look at the major magmatic arcs found in the Philippines. We have 6 main arcs correspond to a different subduction system and contribute to the volcanic geography of our island. So this includes the East Luzon Arc, Central Luzon Arc, Mindoro Panay Arc, Negros Panay Arc, Mindoro Cotabato Arc, and lastly the Zulu Zamboanga Arc. So these arcs reflect the active tectonic boundaries surrounding the Philippines and help explain the distribution of volcanoes across the country. So in this map, we can identify the East Luzon Arc through volcanoes along the eastern side of northern Luzon. The red triangles represent quaternary volcanoes and the red circles which show extinct Mayusan volcanoes. These align along the eastern margin indicating a magmatic arc. Now, if you look at the center right part of the image, you will see a label that says ELT. This most likely stands for East Luzon Trough, which is an important tectonic feature related to the formation of the East Luzon Arc. This arc lies right next to the Philippine Trench, labeled as PT on the map. The East Luzon Arc formed from the westward subduction of the Philippine Sea Plate beneath Earth's eastern Luzon, producing magma and creating a volcanic arc.
Now, in the Central Luzon Arc, it is located in the western and central Luzon, including Zambales and Bataan. It is associated with Manila Trench, formed by the subduction of the South China Sea Plate beneath the western margin of Luzon, and it hosts active volcanoes such as Mount Pinatubo and Mount Mariveles. This focuses on the Central Luzon Arc, a key magnetic arc system located in the western and central regions of Luzon, including areas like Zambales and Bataan. This arc is geologically significant because it's directly associated with the Manila Trench, a major subduction zone. What's happening here is that the South China Sea Plate is being subducted or pushed underneath the western margin of the Luzon Island Arc. This subduction process is what generates magma and leads to the formation of volcanic activity. As a result of this tectonic interaction, the Central Luzon Arc hosts active and historically significant volcanoes, notably Mount Pinatubo, which famously erupted in 1991, and Mount Mariveles, both a rich part of the Bataan volcanic arc. You can see a geological map showing the distribution of different rock types and volcano zones in Luzon. Each color and symbol here represents various geological units, such as volcanic rocks, intrusive rocks, and metamorphic rocks. This helps illustrate the complexity and variety of the geology in the Central Luzon Arc region. Next is the Mindoro Panay Arc. It is located in the southern Luzon, Mindoro to Panay Island. It is now associated with Manila Trench North and Solo Trench South, result of complex interactions involving the subduction of the South China Sea Plate and the Solo Sea Plate. This highlights the Mindoro Panay Arc, which stretches the southern Luzon of Mindoro down to Panay Island in the central Philippines. This arc is geologically unique because it is influenced by two major subduction zones, which is the Manila Trench to the north and the Sulu Trench to the south. The formation of this arc is the result of complex tectonic interactions. Specifically, it's shaped by the subduction of the both China Sea Plate and the Sulu Sea Plate beneath the Philippine Mobile Belt. The map here shows the distribution of various geological units in the region, like volcanic rocks, intrusive rocks, sedimentary formation, and ophiolites, which help us understand the tectonic history and composition of this arc. These complex layers show how dynamic and active this region has been geologically over millions of years. Next is the Negros Panay Arc. It is located in central Visayas, encompassing Negros and Panay Islands, associated with Negros Trench, and is formed by the subduction of the Sulu Sea Plate beneath the Philippine Mobile Belt, and it features active volcanoes like Mount Canlaon, which is part of the magnetic arc system in the central Visayas region. It includes both Panay and Negros Island. This arc is primarily associated with the Negros Trench, an active subduction zone just west in the arc. The magmatic activity in this region is a result of the subduction of the Sulu Sea Plate beneath the Philippine Mobile Belt, a major tectonic feature that runs through the Philippines. As a result of this subduction, the region is volcanically active and features prominent volcanoes such as Mount Calaon, which is one of the most active volcanoes in the country. The map at the top shows the geological layout and tectonic structures, including volcanic zones, sedimentary basins, and the position of the Negros Trench. The cross-section below helps us visualize the subsurface structure, showing how the tectonic plates are interacting underground and where the magma might be generated and rise to the surface. Next is the Mindanao-Cotabato Arc. It is located in the southern Mindanao and associated with Cotabato Trench, resulting from the subduction of Celebes Sea plate beneath the southern Philippine mobile belt. It contains active volcanoes such as Mount Patumtum and Mount Parker. This shows the Mindanao-Cotabato Arc, which is magmatic arc located in the southern Mindanao. It is geologically significant because it's associated with the Cotabato Trench, which you can see here on the map. This magmatic arc formed due to the subduction of the Celebes Sea plate underneath the southern Philippine mobile belt, which, when one tectonic plate is forced below another, like in this case, it causes melting in the mantle, which leads to the formation of volcanoes. As a result, this arc hosts active volcanic centers, including well-known volcanoes like Mount Patumtum and Mount Parker, both of which are shown in the map as part of the active volcanic centers. Overall, the Mindanao-Cotabato Arc is a good example of how a tectonic activity, especially subduction, leads to volcanism in the Philippines. And lastly is the Sulu-Zamboanga Arc. It is located in the western Mindanao in the Sulu archipelago. It is associated with Sulu Trench. It is formed by the subduction of the Sulu Sea plate beneath the Zamboanga Peninsula. It comprises volcanic islands with basaltic compositions, and it represents a less active arc compared to the others in the Philippines. This focuses on the Sulu-Zamboanga Arc, which is located in the western Mindanao and extends in the Sulu archipelago. This arc is geologically linked to the Sulu Trench as seen in the map. It was formed by the subduction of the Sulu Sea plate underneath the Zamboanga Peninsula, just like other magmatic arcs. This subduction process causes the melting of the mantle material, which then rises and forms the volcanic islands. One interesting feature about this arc is that it mostly comprises volcanic islands with basaltic compositions. That means the lava here tends to be low in silica, making it more fluid and resulting less explosive eruptions. Compared to the other arcs in the Philippines, this is considered less active, meaning it has fewer recent eruptions or volcanic activity. Now that we have wrapped things up, I hope you learned something regarding the tectonics of the Philippines. If you have any questions, feel free to comment down below and we can answer them as best as we can. And as always, thanks for watching and listening.